Let's not talk shit this time.
Okay. This is paper 4, crystallization of amorphous cobalt silicon alloys. All right, intro.
Okay.
They did sheet resistance measurements, calorimetric measurements, and their calorimetric measurements helped them understand heat of crystallization, which is, I think, the main, like, their big thing that they were like, we weren't able to find this information anywhere else. Yeah, I have some other stuff like crystallized volume fraction is the peak area at some time t divided by the total area underneath the exothermic peak. Past work was crystallization of amorphous cobalt silicon through ion implantation. They talked about different energies. Does it involve nucleation? Yeah, this is all just background in there. They found random nucleation and growth in amorphous cobalt silicon. This is in past work through co-evaporation and high energy ion implantation. So that's why they're about to use co-evaporation. They talk about an Abrami exponent of 4 in co-evaporation, but in ion implantation they got 3 equaling incomplete amorphization. I think that's the word. The Abrami exponent describes how solids transform from one phase to another at constant temperature. 4 meaning that there's 3 of the contributions are from growth, and the last one is from constant nucleation rate. Yeah, so n equals 1 to 2 is like a distribution of nucleation sites is not random, so happening at like surfaces, edge defects, point sites, etc. And then an Abrami exponent of anywhere from 3 to 4 means that nucleation is random.
It's not more than 3? Like 1 is linear, 2 is like 2-dimensional,
Yeah.
3 is tri-dimensional, more than 3 is just random.
Yeah.
Like they wanna get random things, right?
And I think the thing they wanted to address, or not, or here it was like 4 is like 3 and 4 is different because 4 has this constant nucleation rate while 3 does not. Yeah. So they're reporting on the crystallization of co-evaporated amorphous cobalt silicon alloys across a range of different compositions. They use DSC, TEM, and in situ stress and resistance measurements in order to characterize the physical properties, specifically during the crystallization process. And then they had evidence for structural relaxation, which is the 3D growth for a fixed number of crystals. They have all these different compositions, but they only do work on a couple, which I think I'll touch base on next. Okay, so background information. What is DSC? I'm sure someone who actually uses, I think you use DSC in your research. Okay, so you may be able to fill in. I kind of did DSC work in the past. It was mainly TGA, but like same concept. Measures physical and chemical changes as a function of temperature. You have heat of reaction or your delta H change in enthalpy due to the process of a chemical reaction. So less than 0 is exothermic, greater than 2 is endothermic. So you have 2 like vessels, containers, one containing only your solvent, typically water, the other one containing equal parts solvent and your material. And you would closed system, so no mass flow. You'd heat them at the same temperature, like they're heated with different temperature plates, but they're at the same temperature. And conducted either at constant volume or constant pressure. The heat flow from the reference pan, or the one with only solvent here on the right, is subtracted from this one to be able to get your like net thing. There's a video here from a lab that talks about DSC. It's relating it to polymers, but the concept's still the same, but it was really good because it showed like actual pictures of the DSC instrument, and then this is where I got some of these plots as well. And then there's this like lib text on DSC that I thought was really helpful as well. Yeah, so this is like an example curve. You'll see here like exo up, they'll have exo up or like endo up or endo down or whatever to tell you like what reaction's actually happening. So the bottom curve is the first heating cycle read from left to right, and this analyzes the material as is, so helps you understand like what happened during manufacturing or the production of the material. And then the next curve is read right to left, and it's information on resolidification of the material and ends up erasing any thermal history. And then there's a second heating curve, which is going to be on the next graph.
So the way I understood it when I was taught it, the heat flow is the flow that the machine has on the material in the pan, comparing it to the other pan, right? So what sort of happens in the DSE is I think you're flowing at a constant rate, right? But depending on how your material reacts to the increase in temperature, you have different transitions that can either take up more heat flow from the machine to continue going up, or actually release heat, so less heat flow from the machine is required. When you read this, did you see that exo was up, like exo up and endo?
I'm just pulling this from like a sample graph, like, and they said like exo up meaning an exothermic process resulting in higher values,
Okay.
and endothermic would be lower, versus like they might have a graph that's like endo up, which shows that endothermic processes result in higher values. So I think they're just trying to like help you relate like what's actually happening in your thing.
Okay.
And then these like increases in temperature, determine either like an exothermic reaction happening or endothermic reaction, which is usually your like TC, or like your crystallization temperature.
See, like for me, for my stuff, like my research and like what we do, like this confuses me because we usually do like endo up. So it's like
It's just
To be fair-
depends on the type of research, I guess. But they just mention it.
Yeah.
Yeah.
And
so probably it's a better idea not to mention those things less than 0 exo.
Oh,
More
yeah.
than 0 endo.
This was,
because in our research, it's in this particular paper, it's exo up,
Yeah.
endo down.
Yes, this is like because these are pulled from like this information and this information are pulled from two different things. This one also is pulled from, they were relating it to polymers research, which is probably why they're doing exo up. This is more of like a general, like for my own general sense, like
Yeah, that's just
enthalpy
thermodynamics.
less than 0, general
Yeah, they'll
thermo. This is in
yeah.
like actual relation to like this graph. But yeah, so there's a second heating curve graphed separately, which is the ideal behavior of the material. And this is typically good for my material identification and then being able to compare across materials. This is again, like this had a good show of like fast transition. So again, this is like polymers based, but I think it just like shows the general concept of DSC. Glass transition, low temp crystallization, melting crystallization. So peak temperature and so that's DSC. And then co-evaporation